Hello, it's nice to talk to you today. This presentation will demonstrate some work I did for a client a few years ago where I used interferometry techniques in a low-cost system for direction finding of push-to-talk walkie-talkies. The project objectives were to determine if a low-cost direction-finding interferometry system could be built using COTS hardware, to determine the best mathematical techniques to use, and solve any emergent problems encountered. The presentation consists of the following sections. These will lead us through an overview of techniques, the equipment and mixing methods, a set of potential algorithms and the one finally chosen, the trials and equipment used, and finally, the results and conclusions of the trials undertaken. Direction-finding techniques use phase comparison over an array of antennas for low-bandwidth signals in order to find the RF emitter location. Interferometry is a technique to identify the direction from which an emitter is transmitting a signal. This is based on the phase difference seen between two or more antennas located at a fixed distance apart. To measure the angle of arrival of an incoming signal, we need to know the time difference of arrival of the electromagnetic wavefront of frequency f between two adjacent antennas. The phase interferometer principle relies on the time difference of arrival of a signal at an angle θ from the boresight of an antenna array. At each set of adjacent antennas, place a distance d apart. The differential distance can be expressed in terms of the angle of arrival θ as sin θ equals the differential distance, a, divided by the antenna separation d. Basic geometry yields the necessary equations. A plane wave arriving from an emitter at an angle θ is received by one antenna before another within the array. The time difference can be expressed as a phase difference for the mean emitted frequency. Phi equals 2 pi ft. The difference in path length is a, which equals d sin θ. So, given that a equals ct, where c is the speed of light, then t equals d sin θ divided by c. Substituting this into the phase difference equation yields the phase difference, phi, in terms of the angle of arrival, θ. Given that for a sinusoidal wave of frequency f, c equals f lambda, then phi equals 2 pi d sin θ divided by lambda. So, by rearranging this equation, the angle of arrival θ can be expressed as θ equals sine inverse of lambda phi divided by 2 pi d. Phase interferometry is used when accurate angle of arrival information is required and a single emitter's position needs to be determined. This requires that the interferometer is configured to give an unambiguous field of view in a left-right sense but not a fore and aft one. To achieve this, the angle of arrival θ must be between minus pi over 2 and plus pi over 2. This gives a phase shift between minus pi and plus pi if the distance between the antennas equals lambda divided by 2. A linear array of 4 dipole antennas, consisting of fencing wire and of lengths lambda divided by 2, placed at a distance of lambda divided by 2 apart. These were mounted in a simple wooden beam and supported on a tripod. 4 antennas allowed for up to 3 separate sources to be identified and aided in the rejection of noise which had been encountered before when only 2 antennas had been used. All of the required equipment, apart from the signal generators, was contained inside a waterproof Pelly case. The equipment chosen for this feasibility study was an ETIS Research Universal Software Radio Peripheral, USRP, version 2. This is a software-defined radio which supported multiple RF front-ends by means of modular daughter boards. The WBX board chosen supports the frequency range 50 MHz to 2.2 GHz. The USRP has 2 channels. So, 4 antennas needed to be mixed into 2 in some way to aid in the rejection of noise. The method chosen used 2 signal generators, tuned to 446 and 445.9 MHz, split, and mixed with the RF signal from each pair of antennas. This resulted in a set of heterodyne signals of frequencies of 56.25 and 156.25 kHz for a walkie-talkie channel. The signals were separated in the signal processing software using fast Fourier transforms. This schematic shows the configuration used. For purely direction-finding algorithms, the signal source is considered to be in the far field, and hence, the wavefront of the incoming signal is considered to be parallel and similar for each receiving antenna, except in the sense of time delays induced by the geometry. The amplitude and phase differ across the array. The amplitude variation could be used for range calculations, but the interest here is only in the phase differences. Now the problem is to determine the phase difference from bursts of signals received at each antenna. A number of algorithms were looked at. After due consideration of the simplicity of implementation and the equipment available, the following were chosen. Music. Multiple signal classification. Average music. Extended music averaging eigenvectors. Root music. Solving the music characteristic equation. Esprit. Estimation of signal parameters via rotational invariance techniques. This trigonometrical identity shows that the phase difference between each receiver is preserved after frequency shifting. Heterodyning the signal and filtering out the higher frequencies leaves a frequency difference and the phase shift component. The most appropriate representation for this is in the frequency domain. Here, there is a detailed explanation of the preferred algorithm. The root music algorithm. The algorithm uses the same framework as the music algorithm. Here, X represents a matrix of transformed receiver signals in each row, where A is the steering vector due to time delays and hence phase shifts. F is the complex representation of the signal source, and W is a complex circular Gaussian weakly stationary noise process. A time delay in the frequency domain can be represented as e to the minus j omega delta t. Omega delta t is equivalent to the phase shift, phi. The steering vector A can now be represented as a vector of increasing time delays in line with the delays at each receiver. S is the covariance matrix of the signal matrix X, equivalent to the expectation of X with its Hermitian. S is symmetric and therefore is orthogonal, which means that the eigenvectors are orthogonal. Eigenvectors specify orthogonal subspaces, the signal subspace, and the noise subspace. These correspond to the largest and smallest eigenvalues accordingly. Consider only one transmitter, the steering vector A, and hence the signal subspace, has dimension 1. This is associated with the largest eigenvalue of S. The remaining eigenvalues make up the noise subspace. The noise subspace E is defined by the eigenvectors associated with the 3 smallest eigenvalues. The Euclidean distance from any vector spanning the noise and the signal subspaces to the signal subspace is a complex inner product given by this equation. This is easily demonstrated by considering a 3-dimensional example. The derivation is shown here. The matrix E is shown to be the matrix of eigenvectors associated with the noise subspace. The root music algorithm exploits the squared distance equation by considering its reciprocal, given here by the function p mu of phi. As the distance between the noise subspace and the signal subspace tends towards 0, the p mu of phi function tends towards infinity. The root music algorithm finds the poles of the p-mu of phi function. This is equivalent to finding the zeros of the distance squared equation. Given that a unit delay, z inverse equals e to the minus j theta. Then, the steering vector is formed from these delays. Given the distance squared function represented in this way, a polynomial p of z is generated which has a specific form. As shown here. The coefficients, pi, are the sums of the off-diagonals of the noise subspace matrix product. The roots of this form of polynomial form two sets of reciprocal complex conjugate pairs with the same argument. They form a two-loop interlocked knot on the z-plane, with the crossover rotated by the phase shift of the incoming signal. This crossover has a modulus of 1 and is populated by two of the roots of the polynomial. The other solutions are artifacts of the eigen vector set of the covariance matrix S, which can be considered to have rank 1. Here is an example with an array of 10 antennas. The phase shift is pi divided by 3 and the resultant angle of arrival is sine inverse of phi divided by pi. This equates to an angle of arrival of approximately 19.5 degrees. The trials were carried out on a turntable. They consisted of zeroing the turntable position and then, setting it to a nominal angle to the transmitting device, placed approximately 100 meters from the turntable center. A repeated series of signal transmissions was analyzed as received and stored for analysis. The equipment used can be seen in the following photographs. The antenna, yoke and test rig. The USRP and mixing wiring inside the Pelly case. The Pelly case and signal generators. The final results are presented here. Matched against various statistics, they show a remarkably accurate prediction, with a maximum error of plus or minus 3 degrees. In conclusion, the interferometry method, for determining the angle of arrival, can be achieved with a good degree of accuracy. The accuracy depends on the antenna configuration, the algorithm chosen, the averaged music, esprit, and root music algorithms in conjunction with the Kalman filtering model showed similar remarkable performance over all the linear VHF configurations. The worst-case error for the entire dataset was plus or minus 3 degrees.